All right, let's get started again. Happy to introduce Daniel Smania. We'll talk about the renormalization operator for multimodal maps.
Thank you very much. So I never actually talked with Dennis Sullivan, but I was going to see is going to have a big influence in this presentation. I actually stayed 9 months in Stony Brook in 2002. I just remember one funny story about Sullivan. There is this seminar of dynamical systems, and it's a very small room. And there are very few seats. And once, Sullivan arrived late, and it was full. And there was this little sofa close to the wall. There were 2 people in there, 2 students, I think. So Sullivan just went there and say, "Move," and the guys just run away for their lives. And Sullivan just laid in the sofa in the two spaces and put like this. And I remember this story. And another story is about the work of Sullivan. When I was undergraduate, I was fascinated by purification, universality, and things like that. There are lots of articles in popular magazines about science and things like that. But I didn't find any book about Feigenbaum, Colletterse, conjectures on renormalization, and so on and so forth. But there is this professor in my university, a very small one, that has a lot of books on dynamical systems. So, he was curious about, but probably he never read about the books. And one of these books was One-Dimensional Dynamics by Sebastian Mainstring and Wellington Melo. And the last chapter, that has 1/5 of the size of the book, was about renormalization. And exactly, most of these chapters is actually about the work of Dennis Sullivan on renormalization. So I got a legal copy of this book, and I tried to read the last chapter. And of course, I was doing analysis and point set topology on that time, and I couldn't understand anything, just the preface, just the introduction of the chapter. So I start from the beginning of the book. Maybe it's easier, right? So the beginning of the book was about renormalization of different methods of the circle, Yoccoz results, I think like that, and I couldn't understand either. So I think I decided that maybe I need some help to understand this. And so that last chapter was about the work of Sullivan, was responsible to take me to INPA to work with Wellington. So better or worse, Sullivan work is responsible for me to work in one-dimensional dynamics. Okay, so I'm going to talk about renormalization for multimodal maps. So I wanted to explain renormalization for arbitrary multimodal maps, but actually you can reduce the situation for compositions of unimodal maps, okay? So a deep renormalization, if you pick an infinite normalizable multimodal map, deep renormalizations with large period, are actually compositions of a finite number of unimodal maps, a map like this. So my maps are going to be this. They are going to define in a certain number of intervals, disjoint intervals, and F permutates these intervals, and the map in each one of these intervals are unimodal maps. So this map is renormalizable if you can find a cycle of intervals that are permuted by the action of this map. And I'm going to assume that all the critical points are inside one of these intervals. So what you do is the following. You normalize each one of the intervals that contains the critical points. So I have 3 intervals, the orange, the red, and the green, and they are permuted by the dynamics. So what you do is just to take second iteration in the red interval, you go to the orange one, and 5 iterations go to the green one, and after 2 iterations you go back to the red one. So this is going to be the renormalization of this map. You just normalize these intervals for the original size, and you get a map of the same type. So that's the renormalization in this setting. Okay. So this is a cycle of renormalizations. Here you have 9 intervals that are permuted, and all the critical points belongs to the cycles. Oh, that's bad. And a map is infinitely normalizable, you have infinite many cycles of intervals with the period growing. And the combinatorics is bounded if the sequence does not grow too fast. So the consecutive periods are, the quotient of consecutive periods are bounded by B. So this is bounded combinatorics. So the main theorem, sorry, it's very bad. So the main theorem is the following. Pick a finite dimensional family, smooth family of real analytic multimodal maps. Okay? So you can define the set lambda or set lambda B of the parameters where this map is infinitely normalizable with bounded combinatorics. So the main theorem is the following, that for a generic finite dimensional family, you have that this set has zero Lebesgue measure. Okay? So that is the main result. What I mean by generic, so I need to be careful here. So I just consider, for instance, the interval where the multimodal maps are defined and pick a complex neighborhood of this interval. And you define the Banach space of all the functions that are continuous in the closure of this complex domain, complex analytic inside, and real on the real line. So this is a Banach space with the subnorm. And what I mean by generic, I mean CK families, generic CK families that goes from n-dimensional square to this Banach space. And also I consider real analytic families. So it's not very well described here, but like real analytic families that are continuous in the boundary of this multi-disk. Okay? So generic in these topologies. So you know a lot about renormalization operator for unimodal maps. A lot of work on Douady-Hubbard, Sullivan, McMullen, Lyubich. And for multimodal maps, you know a few things. So there's this thesis of John Hu that about bimodal maps, renormalization for bimodal maps with bounded combinatorics. There's my PhD thesis and article that I published in 2005. It's some work in progress that I'm doing. But this is kind of old stuff. You can prove that using previous arguments by Lyubich, McMullen, Sullivan, and so on and so forth. So you know that if a map is infinitely normalizable with bounded combinatorics, then the renormalization is a pre-compact set. And this is a very, well, this is a much more, well, takes a lot of time to prove that, but the omega limit set of R, so pick all the possible accumulation points of the sequence of renormalizations. So this is an omega limit set of a normalization operator, and the dynamics there is conjugated with a full shift with finite many symbols. Okay? Actually have a very explicit description of the dynamics there, at least in the topological point of view. And you have universality. That means that given any infinite normalizable map with bounded combinatorics, you can find F star inside this omega limit set has exactly the same metric behavior. The two orbits by the renormalization operator converges exponentially fast. This lambda does not depend on the map. The prefactor can depend on the map. So that's we already know. Right. So the steps of the proof of the main theorem is like this. First, you complexify the renormalization operator. This is kind of standard thing right now after work of Lyubich and Avila, Lyubich and Melo. You just use a complex bound, that's this tool developed by Sullivan, to complexify the operator. See, the renormalization operator has an operator, complex analytic operator, in a complex analytic Banach space, a compact one. And the second step, that's the most difficult one, is to prove that the omega limit set is hyperbolic. The third step is to prove that, so you have now hyperbolic set. You can talk about the stable lamination of this hyperbolic set. So what you prove is that if you pick a family of multimodal maps which are transversal to the stable lamination, then the set of parameters with bounded combinatorics, lambda B actually, has zero Lebesgue measure. And this is actually easy because you can use adaptations of the results of Bowen-Huel for finite dimensional case. If you pick a hyperbolic set which has not an attractor in a finite dimensional case, which are at least, let's say, C2, and pick the stable lamination, this is a set of zero Lebesgue measure. So they proved that. So you can adapt this to prove this statement. So it's a totally abstract statement in an infinite dimensional setting. And the last step is to prove the result for genetic families. And this is also surprisingly easy. Using the result for transversal families, you can actually prove the result for genetic families using something very elementary, the Fubini theorem. Okay? So what I mean by Fubini theorem is just that result that, well, something like this. You pick, let's say, in the plane, you pick a set which is 0 Lebesgue measure. So you know that for every vertical line or every horizontal line, the intersection has 0 Lebesgue measure in these real lines. Okay? So it's just that. So this position here. Well, the lamination is to leave is actually holomorphic, right? Real analytic or holomorphic. But the lamination itself is holder, just holders.
But also you can use Fubini theorem.
Yeah, then
you don't use Fubini theorem for the lamination. So the argument involving value, you never use the lamination itself. You just use the families or things like that. So we don't need to use Fubini theorem for the holonomy of the absolute continuous solution.
What is the codimension of the WS animation?
The codimension is the number of unimodal components. So if you have 2 unimodal components, then you have codimension 2. So it's not codimension 1 like in unimodal case. So you cannot use that formation C1. Right. So I know that people are curious about this. People get a little scary when you have infinite dimensional setting and adapt things from finite dimensional ones. But I cannot explain this now. I wanted to concentrate in this.
Continuity of the holonomy map?
No, I just I never use the holonomy map. I just use the family. So the idea is just. So the idea is just pick the family. Okay? And this family, because it's transversal, when you pick that, so the hyperbolic, I don't know how to draw the hyperbolic set, so some counter set inside this. And when you pick this family in the stable that intersect transversally the stable lamination, this guy gets very big. And this is not a attractor, so there are some holes, some macroscopic holes. Then you can pull it back and get holes in all scales here. But you need to be careful, because when you pull it back a ball, you get something that is not round. Okay? But it doesn't matter, because you can use these dynamical balls, like when you calculate metric entropy or things like that. So you don't really need, you just need to make a nice covering of dynamical balls and make the argument in the family. So the argument is always finite dimensional. Just work with the families itself. All right, so I can explain this later if you want. So what I'm going to concentrate in the fact that the Harmonization operator is hyperbolic. So how you prove that? I'm going to use a different argument from Lyubich work on unimodal maps. It's a little different. So first I need to remind you what's a quasi-conformal vector field. A quasi-conformal vector field is just a function, let's say, from C to C, that d bar is uniformly bounded by some constant. So if you don't remember what is d bar, because I usually don't, you see this formula here. So for instance, if d bar alpha is 0 everywhere, you have a holomorphic function. Okay. So why do I need this? To define horizontal directions that was introduced by Lyubich in the work in unimodal case. So if you have a polynomial-like map, if you don't know what's a polynomial-like map, think in a polynomial that everything is going to work more or less. So pick a polynomial-like map. You say that a function is horizontal with respect to this function if there exists a quasi-conformal vector field that satisfies this cohomological equation. Okay? And I also going to assume that d bar is 0. But this is actually, you don't need to worry about this d bar equals to 0, because in your case it's like automatic. You don't have invariant line fields for this map, so don't worry about. So you can define the set of all horizontal vectors with respect to x. So for each f, you have horizontal the set of horizontal directions, that's a vector space. And what's nice about these horizontal directions, they are stable directions for the harmonization operator. So one can prove the following. This was proven by Lyubich in the unimodal case. In the multimodal case, I'm doing that. But this is actually really, it's not very complicated. It's just to make, well, use the arguments of Lyubich in the settings, little adaptations. So you have continuity of these horizontal directions. So for each f, you associate the directions, horizontal directions. This is a continuous thing. The codimension is finite and depends only on the number of unimodal components. You have this vector bundle of the horizontal directions is invariant. If you apply the derivative of the harmonization operator in a horizontal direction, you get horizontal direction. And what's more difficult to prove is the contraction. You have a contraction on the direction, exponential contraction, when you iterate the derivative of the harmonization operator in these horizontal directions. Okay? So this, in the future, I'm going to prove that this horizontal direction is actually the stable direction. Okay? So we know a lot about this. So there's just a finite dimensional transversal to this that we don't know what happens. So we wanted to understand what happens to the directions transversal to the horizontal directions. Good. Okay. So how you do that? How you prove that something is hyperbolic? So let's go back to linear algebra, chapter 0. So pick a hyperbolic, no, it will be fast. So pick a hyperbolic linear map that's invertible. So you have the stable direction, that's the blue thing, and the unstable direction, that's the red thing. So what you know is the following. If you pick, well, I thought that we were going to sleep, so I need something. And so if you iterate the t in the future, you know that if you pick a guy in the unstable direction, this guy grows. And if you pick a guy in the stable direction, when you go backward in the past, this guy grows. And if you pick a vector in the generic position, he grows in the past and the future. So it doesn't matter the vector that you pick, he grows in some direction, except 0. Okay? So this is actually a characterization of hyperbolic. This is so important that I put a blue background in such a way that you cannot see it. So T is hyperbolic if you pick all the vectors that when you iterate in the past and the future, you get a bounded orbit. So you can define this, and it's hyperbolic if only if this is just the 0 vector. So I wanted to use that to my hyperbolic set. So I need a no-autonomous version of this. And fortunately, there are a no-autonomous version of this that was done in the 70s. So we have this. So this is a nice theorem by Sacher and Jarcel in the 70s. And the setting is the following. You pick a compact metric space. And suppose you have a holomorphism in this compact metric space where minimal sets are dense. So it could be a rational rotation, for instance, or a full shift, right, with the density of periodic points. Good. Now, pick a function that associates with x an invertible matrix. And that's continuous. So you can define this skew product, this linear cocycle. Okay? So the only thing that's really important here, the only thing that's different is that assumption on the base. The base, you have this density of minimal sets. So now I can define the sets which, when you iterate x and v, you have a bounded orbit in the future and in the past. Okay? So I can that means that if you pick any point, you can approximate by points in a minimal set.
So the union of all the minimal sets is dense enough.
Exactly. Yeah. The union of all minimal sets are dense.
So for instance, identity manifold.
Don't need to be topological transfer. So okay. So let me put the statement and then I give you examples of this. So the theorem is the following. So the theorem is the following. The theorem is the following. The theorem is not the following. It's not working anymore. Damn. Okay. So the theorem is the following, that T is hyperbolic if and only if, yeah, I know, it's hard to see. So if it's a hyperbolic cocycle, if you only if B is the trivial section, okay? So you don't need, so I'm not saying that the stable direction, and the stable direction has fixed dimension. So you can have, like say, 2 fixed points. Here you have a contraction, here you have expansion. So it could be something like that. So you don't need transitivity or chain recurrence or something like that. Okay, and I state results for skew products, but just because I'm lazy, because you can state for vector bundles as well. Just no need to be a finite dimension. There are results for blank spaces, but it's kind of, there are more assumptions that you need to check. I wanted to use the finite dimensional setting, okay? All right. So back to harmonization. I wanted to use this result for harmonization, but it's infinite dimensional. But I have these horizontal directions that I know what happens. There, the map is already hyperbolic. So what I do is pick the blank space and take the quotient by, the quotient by the horizontal directions. So I get now a finite dimensional vector bundle, and the horizontal directions are invariant by the derivative of the harmonization operator. So I can take the quotient of the action of the derivative of the harmonization operator, and I get a finite dimensional cocycle. And I can apply the result of Sacher and Cell. Okay? So using that, I can prove this result that you cannot see here. That says the following. Now, I cannot iterate backwards because the derivative of the harmonization operator is compact. Okay, in a blank space, it's not invertible. So I can just iterate forward. So if I prove that the sets of vectors V, when you iterate, you have a bounded orbit in the future, coincides with, is contained in the horizontal directions, then I prove that the harmonization operator is hyperbolic. Because I already know that these ones are, you have exponential contraction. So I need to prove the following. I pick a vector in such a way that the iterations are bounded in the future. So I prove that this belongs to the horizontal direction, and then you have exponential contraction. Okay? So that's what I need to prove. Right. So let me restate, wow. Well, let me restate this. I need to prove this. Pick a vector with bounded orbit in the future. I need to prove that there exists a quasi-conformal vector field defined in a neighborhood of the Phility-in-Julia set that satisfies this equation. So that's is the main key lemma. So up to now, I don't use complex dynamics at all, essentially. Well, before for horizontal direction, but not here. Now I come with, I need to construct this alpha by hand. So I'm going to use complex dynamics to do that. And to this, I need the infinitesimal pullback argument. Actually, some of them actually have hair, so I don't know how to draw. Actually, all of them has a different proportion. So to find a quasi-conformal vector field for the solution of that cohomological equation, I just need to solve the equation in the boundary of the domain and in the post-critical set. So I know it's confused, but I want to give an easy situation where I can do that. Okay, so this situation is conform iterated function systems. You have no critical points. Forget critical points. So I have two components. Each one of them is mapped in a conformal way for the whole thing. So the problem is the following. I give a V defining the blue region, and I need to find a quasi-conformal vector field that satisfies the cohomological equation here for every x on the blue regions. Okay? So that's the problem. How you do that? Easy. First, you define in the boundary. That's the main point. Defining the boundary of the domain and from the image. In the domain of the image, you define as 0. And the domain of the, in the frontier of the domain, you define in that way. In this way, you define a function that is a solution for the cohomological equation in the frontier of the domain. Good. Now, you extend this in an arbitrary way between these two things, like a C-infinite function or something. Good. And now, if you have a map, a point y that goes inside the green region after one iteration, you just define alpha using this formula. So automatically, you get that alpha satisfies the cohomological equation in these two green regions. In a repeated process, that's exactly the infinitesimal pullback argument, and you define everywhere. Okay, there's a little step that there's this counter set, the maximum value, so you need to be careful. Okay, but you use some compactness of quasi-conformal vector fields to define in the counter set. So the point is define the first step. Defining the boundary, you are done. You don't have critical points. Good. So I wanted to use that for period doubling maps. And for period doubling maps, you have critical points. So I wanted to get rid of them. So what I do is define an induced map. I define an induced map like this. In this first interval of harmonization, I define it as F. Inside the other interval of harmonization, I have two intervals in the cycle of harmonization. And I define, in this blue interval, I define, thank you. Good. So in this, okay. Okay. Oh, great, good. Oh, sorry. Okay, so in this blue region, I define as the second iteration. And I do this so on and so forth. I get a sequence of domains, blue intervals, where the map is defined with these iterations of the harmonization of the unimodal map. But actually, I want a complex version of this. How you do that? You replace the intervals by balls. It's not exactly balls, but you know, we're late, we're tired. So you replace this by balls. And when you take the first iteration from this ball, you go to this big pink ball. When you pick this ball and iterate, you go to this pink ball here. And you pick this blue ball, you go to this pink one. So you have this nested sequence of blue balls, pink balls, and you have the blue balls converging to the ghost of the critical point. The critical point is disappeared. Good. So that's the map that I want to work with. So I wanted to define the map, the solution alpha, to this induced map instead of the original thing. But now I'm taking iterations, so I need to be careful. I cannot use the same cohomological equation. I need to change a little bit. Because I'm taking iterations, I need to replace V by this ugly thing. You just pick F and make a perturbation in the direction of V and iterate 2 to the power n-1 times and derivate this and take the derivative of t equals to 0. It's an ugly formula, I didn't put it here. But you have this formula for every scale. So you have all these scales, and for each scale you have a formula like that. And you need to find a quasi-conformal vector field that satisfies all these equations in the boundary of, in this boundary and in this boundary here. Okay? So that's what you do. And now normalization comes in. You have a formula, an easier formula for this term. So you can decompose in two parts related with the normalization operator. The first part is the easiest one because it's just you apply the derivative of the normalization operator to V and make a rescaling. Because this is bounded, you are done. The problem is the same in all scales. So you can solve this in an easy way. I don't have time to talk about this part. The funnest part is the second one. The second one, you have almost what you wanted to do, almost the cohomological equation. If you replace this for alpha, you would have a solution. But this beta n depends on n, but it's just a linear function. It's a constant times y. So what I need to do is glue together all these beta n's to get a solution for this. So this is a linear problem to solve the cohomological equation. So I'm going to solve for W1. That is easy. I'm not going to talk about this. My time is finished. So, yeah. I know you guys need to take the bus. So you have WV. WV is easy to solve it. I forgot about this guy. And I need to solve for WV2. Okay? I'm going to explain just this part. We don't have time. Blah, 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 nice, fantastic. Okay, for WV2. For WV2, it's important also this assumption. This assumption implies the following. This constant, I don't have time to explain what is this, but this constant is some Cn, And this Cn does not change too much. So consecutive terms are close, are bounded by, the distance is bounded by a constant C. So I'm going to glue all these linear maps in all scales, define alpha 2 in this way. Is psi depends only on the modulus of x times x, okay? And this psi is going to be like this. You define psi, you pick, all these are circles, are not ellipses actually. You define psi of modulus of x equals 2 Cn in this scale, in all these points. So the function is constant in this ring. And in the next scale, you define has Cn plus 1, but you need just to leave a little room to interpolate this, has a linear interpolation, okay? So psi actually lives in the real line to the real line, so the picture is actually like this. In every scale, the function is constant, and you leave a little room to make a linear interpolation, and that is going to be psi. Okay? Now, this is actually a quasi-conformal vector field if you are a little bit careful. You just need that this interval of interpolation is not small enough in such a way that this, the length of this interval is bigger than the distance to the 0. Okay? So if you have this inequality for every interval of interpolation, you can prove that the quasi-conformality is bounded. Okay? And that solves the problem of the cohomological equation, and that proves that the map is hyperbolic. The normalization operator is hyperbolic. Just to finish, why this proof is nice? First, it's almost infinitesimal. You don't use quasi-conformal maps, Beltran paths, or things like that. Everything works in the derivative of the normalization operator. Second point, that this Saccharin cell thing, steps 3 and 4, don't use complex dynamics or complex structure. It's just smooth dynamics. The third thing that's nice is that most of the proof of the key lemma, the critical point doesn't show up in the proof. You have this conformity-rate dynamical system, work just with this conformity-rate dynamical system, no critical points. That's nice because this gives you hope to study these kind of families where D is not an even number. Okay? I'm not claiming anything, but it's like, no, it's nice. I'm full of hope. And the last step is that this proof is kind of a linear version of the original Lyubich argument. Okay, so that's a nice thing. Oh, sorry for the delay. Thank you very much for attention.
Questions?
You actually prove expansion in the other direction?
Yes, expansion. Yeah, the all transversal directions. Forms from second step.
So how about truly bimodal case?
Oh, okay. So the idea is
What is the question?
because this is for compositions of unimodal maps. Okay. So if you have a map that's not a composition of unimodal maps, what you do with this? So you make an induced map that associates to this bimodal map, for instance, for this composition, so a deep renormalization. And this association is nice. It's a compact operator with dense image.
You can always do that. And always,
Yes, if it's infinitely normalizable, you can always do that. You have this induced map, and you can make this association. And this is a compact map with dense image, and you can use the Fubini trick that I did explain for the original family. You make use a transversal direction here, and use that to use the Fubini trick.
so there should you can reduce one to another.
Exactly. You can reduce the general situation for compositions of unimodal maps. So it's not restriction, actually restriction.
How about unbounded?
Unbounded. Okay, that's really difficult. Yeah, I don't know. I don't know. We cannot certainly use a Saccharin cell because it should be a compact thing. And, but I think that the key is the transversal direction. You don't need universality, actually. I think you need to prove that you have expansion in the transversal direction. Don't care about the universality, and that's enough to prove it. You need some dominant splitting. Dominant splitting for the harmonization operator. If you have this, I think you get, but I don't know how to prove it.
have a real and complex bump for unbounded combinatorics.
You do have, yes. So that's sharing, I think, right?
What is hidden behind the genericity assumption?
What is hidden behind, sorry?
I mean, what do you lose, or what would it cost to not put the genericity?
What cost? Sorry, I didn't understand. Because, I don't know why.
Yeah, but what would you lose, I mean, if you don't make this assumption?
Ah, okay.
Or what?
So they cannot be transversal. Could be like a family that inside the topological class. So you don't change the topological class. So all the parameters are infinitely harmonizable. Bound to number. So that could be a thing that could happen. In CK, if you have a CK family, you can have this. So for an open set of parameters, you are inside the same topological class. So without the genericity assumption for CK families, you cannot do anything. Maybe for complex analytic families. For complex analytic families, real analytic families, you can have a more stronger statement, not just generic. Okay? It would be nice to have something like open and dense. But, I don't think it's possible using this technique.
To check that some vector field is quasi-conformal, you have to sort of check at every point, in a sense, right? So
no, it's an infinitesimal definition, so you can glue together the points. And
what?
it's an infinitesimal thing. So you can, if you have two quasi-conformal maps defining two regions, and the boundary is analytic arc, and the boundary is analytic arc. So you have some suppose that the map is quasi-conformal here and quasi-conformal here, and here the whole thing is continuous. So the map is quasi-conformal everywhere. So you can, exactly what I'm doing here, I'm gluing together linear things with linear maps inside that. So, yeah. It's like,
I thought you were checking that the vector field was
yes,
the d bars in L infinity.
exactly, yes.
So that's a different statement than that. That's for mapping.
So, no, because you can reduce, so if it's piecewise defined and the blunders are analytic maps, it's just to prove, it's just to estimate d bar in each one of the things. Because every removability thing that you have for holomorphic functions, you can have for quasi-conformal vector fields. Because, well, you can integrate things and reduce the problem for holomorphic functions. So this is
State something like that which is relevant for vector fields. This is for mapping. So you're saying if you have something which is piecewise defined outside a finite set of analytic arcs, and it's d bars, infinity inside, then it's okay.
yes. I'm not sure if I understand.
I'm not sure of that.
So
I mean, I don't know. I mean, just for mapping, I know that's okay. But for vector fields,
No, the infinity is not a check piecewise. So you need to know what it is distribution of derivative,
yes.
because don't cause problem. But infinity is
But so I wouldn't worry too much about this because you can actually I make a very rough linear interpolation, but you could smooth things and make the whole thing quasi-conform without problem. So if the problem is the gluing, you can just make some pump function and make the thing work. So it's not a big deal to make a quasi-conformal map C-infinite everywhere, maybe except in the
quasi-conformal mappings I'm happy with. It's just the vector field.
Yeah, quasi-conformal vector field, sorry. So you can make the C2 to be C-infinite everywhere, except in the critical point. So you have a quasi-conformal vector field, except in the critical point. In one point, you have a removability of one point. One points are removable by quasi-conformal vector field.
Yeah, but I think it's something like, dz over z, beautiful on top of the origin, it's holomorphic, but the d bar derivative at the origin is a Dirac function.
need to think about it.
I'm worried you can't just ignore the critical points. You have to know some control. I'm just worried about it. I don't
Okay.
understand.
Yeah.
So he knows that you're
I'm
going
an
to
algebraist now. I don't
Yeah, but this is kind of a.
he knows that your vector field is continuous.
Yes, it's continuous. Certainly, it's continuous. Yes, it's continuous everywhere. Yeah.
And so it is quasi-conformal outside of the single of one point.
Yes. So this is quasi-conformal homology. Yes. You're right. Right.
All right, let's thank Daniel again, and we'll